So here's something you probably haven't thought about in a while. Maybe not since high school. Maybe never. Everything around you right now, the pillow under your head, the walls of your room, the phone you're listening to this on, the glass in your windows, the metal in your bed frame, all of it is made of stuff. And that stuff, that material, has a hidden life. A secret inner architecture that determines everything about how it behaves. Why some things bend and others shatter. Why some things rust and others don't. Why a diamond and the graphite in a pencil are made of the exact same atom, just arranged differently, and yet one is the hardest natural substance on Earth, and the other slides apart so easily you can write with it. That's materials science. And honestly, it's one of the most quietly fascinating corners of engineering, because it sits underneath everything else. You can't build a bridge without understanding steel. You can't make a jet engine without understanding what happens to metal alloys at 1,000 degrees. You can't put a phone in your pocket without understanding semiconductors and glass and lithium and a dozen other materials that had to be coaxed into doing things that nature never quite intended. Materials science is the foundation that every other kind of engineering stands on, and tonight we're going to wander through it together. No rush, no quiz at the end, just the story of how humans figured out what stuff is made of and why it matters. Let's start where it all starts. Let's start with atoms. You already know the basics, right? Everything is made of atoms. Tiny little spheres. Well, they're not really spheres, but we'll get to that. Bonded together in different arrangements. And the type of atom, and the way those atoms connect to each other, and the pattern they form when billions of them stack up together. That's what gives a material its properties. Its hardness, its flexibility, whether it conducts electricity, whether it melts at 200 degrees or 2,000. All of that comes from the atomic scale, which is wild when you think about it, because you're lying there on a mattress that feels solid and continuous. But if you could zoom in far enough, it's mostly empty space. Atoms are almost entirely empty space. The nucleus is this impossibly tiny dense point at the center, and the electrons are way out in these fuzzy probability clouds around it, and the distance between the nucleus and the outer electrons, relative to their size, is like a marble sitting at the center of a football stadium. That's mostly nothing. And yet, here you are, lying on it, and it holds you up just fine. The reason it holds you up is bonds, the forces between atoms. And this is where materials science really begins, because the type of bond between atoms is one of the biggest factors in determining what a material is like. There are a few main types, and they're worth understanding because they explain so much. The first one is the metallic bond, and it's beautifully simple. In a metal, iron, copper, aluminum, gold, the atoms are packed together tightly, and their outer electrons aren't really attached to any one atom. They're shared across the whole structure. Imagine a crowd of people standing shoulder to shoulder, and everyone has let go of their wallets, and all the wallets are just floating around freely between everyone's legs. That's kind of what metallic bonding is like. The atoms form a regular, repeating grid. We call it a crystal lattice, and the electrons flow freely through it like a sea. That electron sea is why metals conduct electricity so well. The electrons can just move, apply a voltage, and they drift in one direction, and that's an electric current. It's also why metals conduct heat well, and why they're shiny. Those free electrons interact with light in a particular way that reflects it back at you. And here's the thing that's really elegant. That free-flowing electron sea is also why metals are ductile, why you can bend them, hammer them into sheets, draw them into wires. When you deform a metal, the atoms slide past each other, and the electron sea just rearranges itself around the new positions. The bonds don't break in a catastrophic way. They just reform. Think about that for a second. The reason a blacksmith can heat up iron and hammer it into a horseshoe is because of the nature of the bond at the atomic level. The atoms slide, the electrons accommodate, and the material reshapes without falling apart. Now compare that to something like diamond, or table salt, or ceramic. These materials have different kinds of bonds, and they behave completely differently. In an ionic bond, that's what holds salt together, sodium chloride, one atom has essentially donated an electron to another atom. Sodium gives up an electron, chlorine takes it. Now sodium has a positive charge, and chlorine has a negative charge, and opposites attract, so they lock together in a rigid crystal lattice, very strong, very stable. But here's the catch. Because the electrons are locked in place, stuck on specific atoms, they can't flow freely. So ionic materials are terrible conductors of electricity in their solid form. Dissolve salt in water, though, and the ions separate and can move around, and suddenly the solution conducts electricity. That's why pure water is actually a pretty poor conductor, but salt water will kill you if you drop a toaster in it. The ions are mobile. And then there's the covalent bond, which is what you find in things like diamond, or silicon, or the carbon-carbon bonds in organic molecules. In a covalent bond, atoms share electrons directly with each other. Not in a delocalized sea like metals, in very specific directional pairs. Two atoms each contribute an electron, and those electrons hang out in the space between them, holding the atoms together. Covalent bonds can be incredibly strong. Diamond is pure carbon, and every carbon atom is covalently bonded to 4 neighbors in a perfect 3-dimensional tetrahedron, and those bonds are so strong and so rigid that diamond is the hardest natural material we know of. But that rigidity comes at a cost. You can't deform diamond the way you can deform copper. There's no electron sea to accommodate rearrangement. If you stress diamond enough, it doesn't bend, it shatters, which is something most people don't realize. Diamonds are hard, yes, but they're also brittle. You can smash a diamond with a hammer. Hardness and toughness are not the same thing, and that distinction is one of the most important ideas in all of materials science. Let me say that again, because it's really worth sitting with. Hardness is about resistance to scratching or indentation, how well a surface resists being permanently dented. Toughness is about resistance to fracturing, how much energy a material can absorb before it cracks apart. A material can be hard but not tough, like diamond or glass, and a material can be tough but not particularly hard, like rubber or lead. The ideal for a lot of engineering applications is something that's both reasonably hard and reasonably tough. And finding that balance, or engineering it, is one of the great ongoing challenges of the field. Now, here's where it gets interesting historically, because humans have been doing materials science for thousands of years without knowing any of this atomic level stuff. The earliest materials engineers were potters and metalworkers and glassmakers, and they figured things out by trial and error, by accident, by generations of accumulated craft knowledge passed down from master to apprentice. And some of what they achieved is genuinely remarkable. Think about bronze, the Bronze Age, roughly 3,300 to 1200 BCE, depending on where in the world you're talking about. Somebody, somewhere, probably in the ancient Near East, maybe in what's now Iran or Turkey, figured out that if you take copper, which is a decent metal but kind of soft, and you melt it together with tin, which is also pretty soft on its own, you get something harder and stronger than either one. That's bronze. And the discovery of bronze changed civilization. Better tools, better weapons, better everything. But here's what those ancient metalworkers didn't know. What they couldn't have known is why the alloy was stronger than the pure metals. They just knew it worked. The reason, and this is beautiful, is that tin atoms are a different size than copper atoms. When you dissolve tin into molten copper and let it solidify, the tin atoms sit in the copper crystal lattice, but they don't quite fit. They're a bit bigger. And those misfit atoms create local distortions in the lattice, little zones of strain around each tin atom. And those strain fields interfere with the movement of something called dislocations, which are... Okay, let's talk about dislocations, because they're one of the most important concepts in materials science, and also one of the most confusing. So, let's take it slow. Imagine you have a perfect crystal, rows and rows of atoms, all perfectly aligned, like oranges stacked neatly at a grocery store. Now imagine you want to slide one layer of atoms over another. That's essentially what happens when a metal deforms, when it bends or stretches. If every atom in that layer had to move simultaneously, breaking all its bonds at once and reforming them one position over, that would take an enormous amount of force, way more force than metals actually require to deform. For decades, this was a genuine puzzle. The theoretical strength of a perfect crystal, calculated from the bond energies, was something like 1,000 times higher than the actual measured strength of real metals. 1,000 times. That's not a small discrepancy. Something was very wrong with the model. And in 1934, 3 people figured it out independently, almost at the same time. Geoffrey Ingram Taylor in England, Egon Orowan, a Hungarian physicist working in Germany, and Michael Polanyi, also Hungarian. All 3 of them, within the same year, proposed the concept of the dislocation. The idea is this: a real crystal isn't perfect. It has defects, and one particular kind of defect is a dislocation. Essentially an extra half-plane of atoms wedged into the lattice, like if you took that neat stack of oranges and shoved an extra partial row in from one side. The lattice is distorted around that extra half-plane, and when you apply a stress to the crystal, that dislocation can move. It doesn't require all the bonds to break at once, just the bonds right at the dislocation line, one row at a time, unzipping and rezipping as the dislocation glides through the crystal. It's like moving a heavy rug across a floor. If you try to slide the whole rug at once, you need a huge force, all that friction. But if you put a wrinkle in the rug and push the wrinkle across, the rug moves with much less effort. The wrinkle is the dislocation. And that's why real metals are so much weaker than the theoretical prediction for a perfect crystal. They're full of dislocations, and those dislocations move easily. Now, and here's where it comes full circle, if you want to make a metal stronger, you need to make it harder for dislocations to move. And one way to do that is to put obstacles in their path. Foreign atoms. Atoms of a different size, like tin and copper. Those misfit atoms create strain fields that impede dislocation motion, and the metal gets harder. That's solid solution strengthening. That's why bronze is harder than copper. That's why steel, iron with a little bit of carbon, is harder than pure iron. Ancient metalworkers discovered the effect. Modern materials scientists understood the mechanism. Thousands of years apart, same phenomenon. And carbon in iron, that's the big one. That's the one that changed everything. Because steel, which is fundamentally just iron with a small amount of carbon dissolved in it, is arguably the most important engineered material in human history. And the story of how people learned to make it and control it and understand it stretches from ancient swordsmiths in India and China and the Middle East all the way to the blast furnaces of the Industrial Revolution and the skyscrapers of the 20th century. The story of steel is really the story of civilization learning to control the atomic structure of a material, even before anyone knew atoms existed. And it starts with iron. Pure iron is actually kind of mediocre as a structural material. It's softer than bronze in many cases. The reason iron eventually replaced bronze wasn't that iron was better. It was that iron ore was far more abundant and tin was getting scarce. But iron on its own wasn't enough. What made the difference was learning to add just the right amount of carbon, and then learning to heat it and cool it in just the right way. And that's where things get really fascinating, because iron doesn't just sit there being one thing. Iron is a shapeshifter. It changes its crystal structure depending on temperature, and that fact, that single quirk of atomic physics, is arguably why modern civilization looks the way it does. Let me explain what I mean. Most metals have one crystal structure, and they stick with it. Copper is face-centered cubic, all the way from room temperature up to its melting point. Aluminum, same deal. But iron is different. At room temperature, iron arranges itself in what's called a body-centered cubic structure. Picture a cube with an atom at each corner and one atom right in the center. That's it. Nice and open, relatively speaking. But heat iron up past about 912 degrees Celsius and something remarkable happens. The atoms rearrange themselves. They shift into a face-centered cubic structure, a cube with atoms at the corners and also in the center of each face. More atoms packed into a tighter arrangement. This high-temperature form of iron is called austenite, named after Sir William Chandler Roberts Austen, a British metallurgist working in the late 1800s. The room temperature form is called ferrite. Now here's the thing that matters. That face-centered cubic structure, austenite, has bigger gaps between its atoms. Bigger interstitial spaces, if you want the technical term. And carbon atoms, which are small, can fit into those gaps much more comfortably than they can fit into the tighter body-centered cubic structure of ferrite. So when you heat iron up into the austenite range and there's carbon present, the carbon dissolves in. It tucks itself into those interstitial spaces between the iron atoms. Everything's cozy, but then you cool it down. And this is where the magic happens. If you cool it slowly, the iron wants to transform back to its body-centered cubic structure, and as it does, it has to reject most of that carbon because there just isn't room for it anymore. The carbon gets pushed out and forms a separate compound, iron carbide, also called cementite, which has the chemical formula Fe3C. 3 iron atoms for every carbon atom, locked together in a hard, brittle crystal. And what you end up with is a mixture of soft ferrite and hard cementite, arranged in alternating layers so thin they're measured in fractions of a micrometer. Under a microscope, these layered structures look like fingerprints, and they're called pearlite, because early metallographers thought they had a pearly, iridescent sheen. Pearlite is a beautiful compromise. It's harder than pure iron, but still reasonably tough, because the soft ferrite layers can absorb some deformation, while the hard cementite layers resist it. But here's what's really clever about steel, and what the ancient swordsmiths figured out by trial and error, long before anyone had a microscope. If you don't cool it slowly, if you cool it fast, if you quench it by plunging that red-hot steel into water or oil, something completely different happens. The iron atoms want to transform back to body-centered cubic, but you're not giving them time. The carbon atoms are trapped. They can't diffuse out fast enough to form cementite. So the iron tries to make the transformation anyway, and what you get is a distorted, strained crystal structure called martensite. It's technically body-centered, but the trapped carbon atoms force it into a slightly elongated shape. Body-centered tetragonal, if you want to be precise. And martensite is incredibly hard, incredibly strong, but also incredibly brittle. It's like glass in some ways. It resists deformation fiercely, but when it does finally give way, it shatters rather than bending. Think about what that means for a swordsmith in Damascus or in feudal Japan. You've got this material that you can make soft enough to shape by heating it up and cooling it slowly, or you can make it hard enough to hold a razor edge by heating it up and cooling it fast. Same material, same chunk of iron with a bit of carbon in it. Completely different properties, just by controlling the cooling rate. That's not chemistry. You're not adding or removing anything. That's heat treatment. You're controlling the atomic structure of the material through temperature and time. And the Japanese swordsmiths, the ones making katanas, they understood this intuitively. They would coat the spine of the blade with clay before quenching, so the spine cooled slowly and stayed relatively soft and tough, while the edge cooled fast and became hard martensite. One single blade with two different microstructures, optimized for two different jobs. The spine needs to absorb impacts without breaking. The edge needs to cut without dulling. Same steel, different heat treatment, different properties. That's materials engineering at its finest, performed by craftsmen who had no concept of crystal structures or phase transformations, but who had centuries of accumulated empirical knowledge passed down from master to apprentice. Now, martensite is too brittle to use as is in most applications. A sword made entirely of untempered martensite would shatter on first contact. So there's a second step. Tempering. You take your quenched martensitic steel and you heat it back up, but only part way. Maybe to 200 degrees Celsius, maybe to 400, depending on what you want. This gives the carbon atoms just enough thermal energy to start diffusing out of the strained martensite lattice and forming tiny, fine particles of cementite. The martensite relaxes. It loses some hardness, but gains significant toughness. And by controlling the tempering temperature, you control the trade-off. Low tempering temperature, you keep most of the hardness, good for cutting tools and files. High tempering temperature, you sacrifice more hardness, but gain much more toughness, good for springs and structural components that need to flex without breaking. This is the basic toolkit of steel metallurgy, and it was all worked out empirically over centuries. But the scientific understanding, the why behind all of it, that came much later. And one of the key figures in that story is Henry Clifton Sorby, an English geologist and microscopist from Sheffield, which is fitting because Sheffield was the steel capital of England. In the 1860s, Sorby did something that nobody had really thought to do before. He took samples of steel, polished them to a mirror finish, etched them with acid, and looked at them under a microscope. And what he saw changed everything. He saw structure. He saw that steel wasn't a uniform, homogeneous material. It was a landscape of distinct phases, grains, and boundaries. He could see the pearlite, the ferrite, the differences between quenched and slowly cooled steel. He essentially invented metallography, the science of examining the microstructure of metals. And here's the thing about Sorby. He was largely ignored. The steel industry at the time was run by practical men who trusted their furnaces and their instincts, and they didn't see much use for a geologist peering at metal through a microscope. His work was presented to scientific societies and met with polite indifference. It wasn't until decades later, when people like Robert Austin and others built on his foundations, that the scientific community really grasped how important microstructure was. Sorby died in 1908, and by then the field he'd pioneered was finally flourishing. But he spent most of his career as a wealthy amateur whose most important insights were ahead of their time. The person who really systematized the science of steel phases was Josiah Willard Gibbs, the American physicist, though he never worked with steel directly. In the 1870s, Gibbs developed the thermodynamic framework, the phase rule, and the concept of free energy that explains why materials form the phases they do at given temperatures and compositions. His work was abstract, deeply mathematical, and published in an obscure Connecticut journal that almost nobody read. But it provided the theoretical backbone for everything that followed. When metallurgists eventually started constructing phase diagrams, those maps that show you which phases are stable, at which temperatures and compositions, they were building on Gibbs's thermodynamics, whether they knew it or not. The iron-carbon phase diagram, which is arguably the single most important diagram in all of materials science, was gradually assembled over the late 1800s and early 1900s through the combined work of dozens of researchers. Robert Austin contributed enormously, as did the German metallurgist Adolf Martens, whose name gave us the term Martensite. If you've ever seen this diagram, and if you haven't, just imagine a map with temperature on the vertical axis and carbon content on the horizontal axis, with different regions labeled for the different phases that are stable under those conditions. It tells you everything you need to know about how steel will behave. It tells you at what temperature austenite forms, where ferrite is stable, where cementite starts to precipitate. What happens at the critical carbon content of about 0.76%, where you get pure pearlite? It's a recipe book, a roadmap, and a physics textbook all in one. But phase diagrams only tell you about equilibrium. What happens if you give the material infinite time to reach its most stable state? And as we just talked about with quenching and martensite, some of the most useful things in metallurgy happen precisely because you don't let the material reach equilibrium. You trap it in a metastable state. You freeze in a structure that thermodynamics says shouldn't exist at room temperature, but kinetics, the speed of atomic movement, says can persist indefinitely because the atoms simply don't have enough energy to rearrange themselves. Martensite is thermodynamically unstable. Given enough time and enough heat, it would decompose into ferrite and cementite. But at room temperature, those carbon atoms are stuck. They're frozen in place, straining the lattice, making the steel hard. And that interplay between thermodynamics and kinetics, between what a material wants to do and what it actually has time to do, that's one of the deepest and most beautiful ideas in all of materials science. It shows up everywhere, not just in steel. It shows up in glass, which is really a liquid that cooled too fast to crystallize. It shows up in certain aluminum alloys that get stronger over time as atoms slowly migrate into clusters. It shows up in the semiconductors in your phone, where carefully controlled diffusion of dopant atoms creates the electrical properties that make transistors work. And it all comes back to this idea that the structure of a material, the arrangement of its atoms, determines its properties, and that structure is controlled not just by composition, but by processing, by what you do to it, how you heat it, how you cool it, how you deform it, how long you wait. That's the central dogma of materials science, if you want to call it that. Composition plus processing determines structure, and structure determines properties. And nowhere is that more dramatically illustrated than in what happened when the age of steel met the age of mass production, when engineers started building things on a scale that had never been attempted before. Railways spanning continents, bridges leaping across rivers that everyone said couldn't be crossed, and buildings climbing toward heights that would have seemed like fantasy just a generation earlier. Because when you start building big, you start discovering failure modes that nobody anticipated, and some of those failures were catastrophic. And I mean that in the most literal sense. Sudden, total, without warning. Think about what that means for a moment. You're an engineer in the late 1800s. You've got this incredible material, steel, and you understand some of its properties. You know how to make it harder, how to make it tougher. You've got heat treatments, you've got alloy recipes, but you're building structures that are orders of magnitude larger than anything that's come before. And the truth is, you don't fully understand how materials fail at that scale. You understand breaking a test bar in a laboratory. You do not yet understand what happens when millions of pounds of load are distributed across a complex structure, day after day, year after year, through winter cold and summer heat, through vibrations and wind, and the slow accumulation of invisible damage. And this is where the story gets both tragic and fascinating, because the failures that happened during this period didn't just kill people. They fundamentally changed how we think about materials. They forced the creation of entirely new branches of science, and some of the most important lessons were learned in the worst possible way. Let's start with something you've probably never thought about, but that shaped the modern world. Fatigue. Not the kind you feel right now, lying there, though that kind is perfectly welcome. I mean metal fatigue, the phenomenon where a material can break under a load that's well below its supposed strength, simply because that load has been applied and removed over and over and over again. The person who first really grappled with this was a German railway engineer named August Wöhler. In the 1850s and 1860s, railway axles were breaking. Not occasionally, regularly. Trains were derailing because their axles would snap clean in two, and when engineers examined the broken pieces, they were baffled. The steel was good steel. The axles weren't overloaded. The fracture surfaces didn't look like what you'd see if you just pulled a bar apart in tension. Instead, they had this strange appearance, a smooth, almost polished region covering most of the cross-section, and then a small, rough area where the final break had occurred. It looked as if the metal had been slowly cracking for a long time before it finally gave way. And that's exactly what was happening. Wöhler set up a testing machine, a beautifully simple device really, where he could apply a bending load to a specimen and rotate it. So the material experienced tension on one side, then compression as it spun around, then tension again, over and over, millions of cycles. And what he found was remarkable. Below a certain stress level, the steel could survive essentially forever, millions upon millions of cycles without breaking. But above that threshold, it would eventually crack and fail, even though the stress was far below what would break it in a single pull. And the higher the stress, the fewer cycles it took. He plotted this as a curve. Stress on one axis, number of cycles to failure on the other. And that curve, the SN curve, the Wöhler curve, is still one of the most important tools in engineering. Every bridge you drive over, every airplane you fly in, every car you ride in. Someone has used fatigue data to make sure the critical components will survive the number of loading cycles they'll experience in their lifetime. And it all goes back to a guy watching railway axles snap in the 1850s. But here's what's really interesting about fatigue from a materials science perspective. Why does it happen? What's actually going on inside the metal? And this took a long time to figure out. The answer, it turns out, goes right back to those dislocations we talked about earlier. When you load and unload a metal cyclically, dislocations move back and forth. They pile up. They interact. They create tiny localized regions of damage, usually at the surface of the material, where stress concentrations are highest. Eventually, a tiny crack nucleates, often at a surface scratch, a machining mark, an inclusion, some little imperfection. And once that crack exists, each loading cycle opens it up just a tiny bit, advances it just a little further into the material. The crack grows slowly, steadily, relentlessly, and the material gives you absolutely no warning. It doesn't bend, it doesn't deform visibly, it just quietly cracks, cycle after cycle, until the remaining cross-section is too small to carry the load. And then it breaks. Suddenly, catastrophically. That smooth region on those broken railway axles, that was the fatigue crack, growing slowly over thousands of miles of travel. The rough part? That was the final, sudden fracture. And the terrifying thing is, the axle looked perfectly fine right up until the moment it didn't. This idea that damage can accumulate invisibly inside a material was genuinely new and genuinely unsettling, and it's still one of the hardest problems in engineering. How do you inspect for something you can't see? How do you predict when something will fail if the failure starts from a microscopic flaw? This is why we have non-destructive testing today: ultrasonic inspection, X-ray inspection, magnetic particle inspection. Entire industries exist because August Wöhler watched axles break and asked why. Now, fatigue is one kind of failure that the age of mass-produced steel revealed. But there's another one that's even more dramatic, and it took even longer to understand. And that's brittle fracture. Here's the thing about steel that makes it so useful. It's tough. It deforms before it breaks. If you overload a steel beam, it bends. It gives you warning. You can see it sagging, you can hear it groaning, and you have time to get out of the way. That's ductile behavior, and it's one of the great safety features of steel construction. But under certain conditions, and this is what took decades to fully understand, steel can become brittle. It can shatter like glass. No warning, no bending, just sudden, explosive fracture. The conditions that cause this are a combination of things: low temperature, high loading rate, and the presence of a crack or a notch. And the history of learning this lesson is written in disaster after disaster. One of the most dramatic examples happened not on a bridge or a building, but on ships. During World War II, the United States embarked on one of the most ambitious industrial programs in history: the mass production of Liberty ships. These were cargo vessels, designed to be built fast and cheap to replace the ships being sunk by German U-boats in the Atlantic. And they were built using a relatively new technique: welding instead of riveting. Riveted ships had their hull plates overlapped and fastened with rivets. Welded ships had their plates butted together and joined by continuous weld seams. Welding was faster, cheaper, and produced a lighter, more efficient structure. It seemed like a no-brainer. But there was a problem. Of the roughly 2,700 Liberty ships built, about 1,500 experienced significant fractures in their hulls. And in some cases, at least a dozen, the ships broke completely in two. Just snapped. Sometimes in port, sometimes at sea. The T-2 tanker Schenectady broke in half while sitting calmly at its fitting-out dock in Portland, Oregon, in January 1943. The air temperature was about -4 degrees Celsius. There was a loud report, like a gunshot, and the ship's deck and sides cracked from gunwale to gunwale. The ship jackknifed, its bow and stern settling into the water while the middle sagged. And this was a brand new ship. It had been in the water for about 2 weeks. Now, you might think this was a welding problem, and in a sense it was. But not in the way you might expect. The welds themselves were often fine. The real issue was more subtle and more fundamental. In a riveted ship, a crack that starts in one plate stops at the edge of that plate. The rivet holes and the gaps between plates act as natural crack arresters. The crack simply can't propagate from one plate to the next. But in a welded ship, the hull is essentially one continuous piece of steel. A crack that starts at a stress concentration, a hatch corner, a weld defect, a sharp geometric transition, can run right through the weld and into the next plate and the next and the next. There's nothing to stop it. And in cold weather, when the steel becomes brittle, that crack can propagate at nearly the speed of sound in the material, thousands of feet per second. The entire hull fractures in a fraction of a second. This was the birth of fracture mechanics as a serious engineering discipline. A man named George Irwin, working at the Naval Research Laboratory in the 1950s, built on earlier work by A. Griffith, who had studied the fracture of glass back in 1920, and developed the mathematical framework we still use today. Griffith's insight had been elegant. He asked a simple question. We know that the theoretical strength of a material, based on the forces between its atoms, is enormous, far higher than what we actually measure. So why are real materials so much weaker? His answer was flaws. Tiny cracks, scratches, voids. These flaws concentrate stress at their tips, and when the stress at the tip of a flaw exceeds what the atomic bonds can bear, the crack grows. Griffith worked out the energy balance. The energy released by the crack growing has to exceed the energy required to create new surfaces. And he could predict the fracture strength of glass quite accurately. But Griffith's theory didn't work well for metals, because metals aren't perfectly brittle. Even when steel fractures in a seemingly brittle way, there's a little zone of plastic deformation right at the crack tip. The dislocations move, the material yields locally, and that absorbs energy. Irwin's genius was incorporating this plastic zone into the analysis. He defined something called the stress intensity factor, usually written as K, which describes the severity of the stress field around a crack tip. And he showed that a material has a critical value of this factor, called the fracture toughness, below which a crack won't grow catastrophically. You can measure this property in a lab, just like you measure strength or hardness. And once you know it, you can predict whether a given crack in a given structure under a given load is safe or dangerous. Think about what that means. Before fracture mechanics, you designed structures by making sure the average stress was below the material's strength. After fracture mechanics, you designed structures by assuming cracks exist, because they always do, and making sure those cracks won't grow to a critical size during the structure's lifetime. That's a completely different philosophy. It's called damage-tolerant design, and it's how we design airplanes, pressure vessels, pipelines, and nuclear reactors today. Every time you fly, you're trusting fracture mechanics. The airplane has cracks in it. I promise you it does. But engineers have calculated how fast those cracks will grow under the fatigue loading of repeated pressurization cycles, and they've scheduled inspections to catch them before they reach a critical size. The whole system depends on understanding how cracks behave in real materials, and notice how all of this connects back to what we were talking about earlier: structure determining properties. The fracture toughness of a steel depends on its microstructure. Tempered martensite has different toughness than pearlite. Fine-grained steel is tougher than coarse-grained steel. Steel at room temperature is tougher than the same steel at -40 degrees, because at low temperatures, the dislocations can't move as easily. The plastic zone at the crack tip shrinks, and the material behaves more brittlely. That's why those Liberty ships cracked in cold weather. The steel they were made from, a perfectly ordinary carbon steel, had a ductile to brittle transition temperature that was right around the temperatures those ships were experiencing in the North Atlantic in winter. Above that transition temperature, the steel was tough and forgiving. Below it, the steel was brittle and treacherous, and nobody had thought to check, because nobody had really understood that this transition existed or that it mattered. This ductile to brittle transition is one of those concepts that sounds abstract until you realize it's the reason certain steels are specified for certain applications. The steel in a pipeline running through Alaska is not the same grade as the steel in a building in Miami, and a big part of the reason is the transition temperature. You want that transition to be well below the coldest temperature the structure will ever experience, and you control it through composition and processing, through the amount of carbon, the alloying elements, the grain size, the heat treatment. Manganese lowers the transition temperature. Carbon raises it. Fine grains lower it. It's all about making it easier or harder for dislocations to move at the crack tip. So here we are, and we've gone from atoms and bonds to crystal structures, to dislocations, to phase transformations, and now to cracks and fractures. And every step of the way, the same principle keeps showing up. The behavior of a material is determined by what's happening at scales you can't see with your naked eye. And the engineers and scientists who figured this out did so, in many cases, because something terrible happened and they had to understand why. There's a saying in engineering that regulations are written in blood, and in materials science, that's uncomfortably close to the truth. But failure analysis isn't the only way materials science advanced during the 20th century. There's another thread running through this story, one that's quieter, but in some ways even more transformative, and it starts with a question that seems almost philosophical. Can we design materials from scratch? Not just discover them, not just stumble onto useful alloys by trial and error, but actually sit down and say, I need a material with these specific properties, and then figure out how to make it. And the answer to that question begins with a group of materials that are about as different from metals as you can get. Materials held together not by metallic bonds or ionic bonds, but by something else entirely, something that would eventually lead to covalent bonds. That's the word, covalent. And covalent bonding is, in a way, the most intimate kind of bond in all of chemistry. With metallic bonds, remember, you've got this sea of electrons shared across the whole material, everybody pooling their resources. With ionic bonds, one atom just hands over electrons to another, and they stick together through electrostatic attraction. But covalent bonds are different. In a covalent bond, two atoms share a pair of electrons between them, and only between them. It's not communal, it's not a transaction, it's a partnership. Two atoms, each contributing one electron to a shared pair, and that pair of electrons spends most of its time in the space between the two nuclei, holding them together. It's direct, it's strong, and it's directional, meaning the bond points in a specific direction in space, and that directionality is what makes covalent materials so fundamentally different from metals. Think about diamond for a second. Diamond is pure carbon, every atom bonded to 4 neighbors in a perfect tetrahedral arrangement, each bond a covalent bond, and those bonds are incredibly strong. That's why diamond is the hardest natural material we know of. But here's the thing. Diamond is also brittle. Hit it the right way and it'll shatter. And it doesn't conduct electricity, at least not under normal conditions, because there's no sea of free electrons. Every electron is locked up in a bond, doing its job, not wandering around. So you get this material that's extraordinarily hard, transparent, electrically insulating, and thermally conductive all at once. A completely different package of properties from any metal, and it all comes down to the nature of that bond. But diamond isn't the covalent material that changed the world. The ones that really matter, the ones that reshaped the 20th century, are polymers. And to understand polymers, you need to understand one particular trick that carbon can do, which is form long chains. Carbon has 4 bonding sites, 4 electrons it can share, and it turns out carbon atoms are perfectly happy bonding to other carbon atoms over and over, forming chains that can be tens of thousands of atoms long. And along those chains, you can hang other atoms: hydrogen, oxygen, nitrogen, chlorine, fluorine, and depending on what you hang where, you get radically different materials: polyethylene, polypropylene, PVC, nylon, Teflon, polycarbonate, polyester. Every one of these is a long carbon chain with different side groups, and every one has different properties. Same basic architecture, wildly different behavior. That's the beauty of it. Now, people had been encountering natural polymers forever without understanding what they were. Rubber, silk, cellulose, DNA. These are all polymers. But the idea that these materials were actually made of enormous chain-like molecules was controversial for a surprisingly long time. And the person who finally settled the argument was a German chemist named Hermann Staudinger. In the early 1920s, Staudinger proposed that materials like rubber and cellulose were made of what he called macromolecules, giant molecules with molecular weights in the tens of thousands or even hundreds of thousands, and the chemistry establishment basically laughed at him. The prevailing view at the time was that these materials were just aggregates of small molecules stuck together by some vague intermolecular force, not true molecules at all. One prominent chemist reportedly told Staudinger to drop this nonsense about giant molecules because there was no such thing. The idea that a single molecule could contain thousands of atoms seemed absurd to people trained in classical chemistry, where molecules were neat little things with precise formulas. But Staudinger was stubborn. He spent the better part of 2 decades gathering evidence, viscosity measurements, chemical analysis, careful degradation experiments, where he'd break the chains and show that the fragments were still large. He coined the word macromolecule in 1922, and he just kept pushing. And gradually, the evidence became overwhelming. By the 1930s, other researchers were coming around. Wallace Carruthers at DuPont was synthesizing entirely new polymers in the lab, building chains from scratch, and the properties of those chains matched exactly what Staudinger's macromolecular theory predicted. Staudinger eventually won the Nobel Prize in Chemistry in 1953, more than 30 years after his original proposal. He was 72 years old. Sometimes being right just takes patience. And here's where it connects back to everything we've been talking about. Remember the central dogma: composition plus processing determines structure, determines properties? In polymers, that principle plays out in ways that are almost more dramatic than in metals. Because with polymers, you don't just have composition to play with. You have chain length, chain branching, the arrangement of side groups along the chain, the degree to which chains are tangled up with each other, and whether those chains are crystalline or amorphous or some mixture of both. And every one of those variables changes the properties. Let me give you an example. Polyethylene, the simplest synthetic polymer, just a chain of carbon atoms with hydrogen, atoms hanging off each side. If you make polyethylene with long, straight chains that can pack tightly together, you get high-density polyethylene, HDPE. It's rigid, strong, opaque, and it's what your laundry detergent bottles and cutting boards are made of. But if you make polyethylene with lots of short branches sticking off the main chain, those branches prevent the chains from packing tightly, and you get low-density polyethylene, LDPE. Same chemical formula, same atoms, but the chains can't organize as well, so it's softer, more flexible, more transparent. That's your plastic grocery bags, your cling wrap. Same composition, different processing, different structure, different properties. The central dogma, again. And crystallinity in polymers, that's a fascinating concept. In metals, we talked about atoms arranging themselves into crystal lattices, nice, orderly rows. Polymers can do something similar, but it's much harder because you're trying to get these long, floppy, tangled chains to line up neatly. It's like trying to get a drawer full of cooked spaghetti to organize itself into parallel rows. Some of it will line up, especially if the chains are regular and straight, but a lot of it won't. So most polymers are semi-crystalline. They have little regions of crystalline order embedded in a matrix of amorphous, tangled chains. And the ratio of crystalline to amorphous determines a huge range of properties: stiffness, transparency, melting behavior, chemical resistance. More crystallinity means stiffer, stronger, more opaque, higher melting point. Less crystallinity means more flexible, more transparent, and the material tends to soften gradually rather than having a sharp melting point. Now, while Staudinger was fighting his battles in academia, something remarkable was happening in industry. The early 20th century saw an explosion of synthetic polymer development, and much of it was driven by the search for substitutes. Celluloid, one of the first synthetic plastics, was developed in the 1860s, partly as a replacement for ivory and billiard balls. I love that detail. The entire plastics revolution arguably started because people wanted cheaper billiard balls. Bakelite, invented by Leo Baekeland in 1907, was the first fully synthetic polymer made from phenol and formaldehyde, and it was a thermoset, meaning once it hardened, you couldn't melt it again. The chains were cross-linked, bonded to each other in a permanent three-dimensional network, and that made it heat-resistant, electrically insulating, and incredibly useful for everything from telephone housings to electrical components. Baekeland became wealthy, and Bakelite became so ubiquitous that the period from about 1930 to 1950 is sometimes called the Age of Bakelite. But the real revolution came with thermoplastics, polymers that could be melted and reshaped over and over. Nylon was the star. Wallace Carothers, working at DuPont's research lab in Wilmington, Delaware, synthesized nylon in the mid-1930s. Carothers was a brilliant organic chemist, deeply influenced by Staudinger's macromolecular theory, and he set out to build polymers by design, Not by accident, not by trial and error, but by understanding the chemistry of chain-building reactions and deliberately choosing monomers that would produce chains with specific properties. He wanted a synthetic fiber that could replace silk, and nylon was the result. Strong, elastic, resistant to mildew and insects, and drawable into fine filaments. When nylon stockings went on sale in 1940, they sold out almost immediately. 4 million pairs in 4 days. But Carruthers never saw that success. He suffered from severe depression throughout his life, and he took his own life in April 1937, at the age of 41, 2 years before nylon was publicly introduced. It's one of the saddest stories in the history of materials science. A man who fundamentally changed how we think about designing materials, who proved that you could sit down with a theory, choose your building blocks, and create something entirely new with predictable properties. And he didn't live to see the impact. His work, though, established the template that the entire polymer industry would follow. You don't just discover polymers, you design them. And that idea, designing materials from scratch, was about to extend far beyond polymers. Because around the same time that Carruthers was building nylon chains in Delaware, other researchers were starting to think about a completely different class of materials, ones that weren't metals and weren't polymers and weren't ceramics in the traditional sense. Materials where the interesting properties didn't come from the bulk of the material at all, but from its electronic structure, from the way electrons occupied energy levels in a crystal. And these materials would turn out to be the most consequential invention of the 20th century. They were called semiconductors, and the story of how people figured out what they were and how to use them starts, oddly enough, with a cat's whisker and a chunk of galena crystal sitting on a radio hobbyist's workbench in the 1900s, a setup so finicky and unreliable that most people gave up on it within a few years. That's where we left off. This strange, temperamental little device that barely worked and yet contained within it the seed of everything that would come after. Computers, smartphones, solar panels, LED lights, the entire digital world. All of it traces back to people trying to understand why certain crystals behaved so strangely with electricity. So, let's talk about what was actually happening on that workbench. A cat's whisker detector was about as simple as an electronic device could be. You had a small chunk of a mineral, usually galena, which is lead sulfide, and you touched a thin, springy wire to its surface. That wire was the cat's whisker, and if you found just the right spot on the crystal, just the right pressure, the device would rectify a radio signal, meaning it would allow current to flow in one direction but not the other. That's what you need to pull audio out of a radio wave. You need to strip away half the oscillation, essentially, and a rectifier does that. But here's the thing. Nobody really understood why it worked. You'd sit there with tweezers, nudging this tiny wire across the surface of the crystal, and most spots did nothing useful. And then suddenly you'd hit a sweet spot, and your headphones would come alive with a radio broadcast. Move the wire a fraction of a millimeter, and you'd lose it. It was maddening. And when vacuum tubes came along in the 1910s and 20s, devices that were bulky and power-hungry, but at least reliable, most engineers happily abandoned crystal detectors and never looked back. But not everyone. A few physicists kept poking at the question. Why did some crystals conduct electricity a little, but not a lot? Why did they rectify? Why were they so sensitive to impurities and surface conditions? These weren't metals, which conduct beautifully. They weren't insulators, which block current entirely. They were something in between, and the existing theories of electrical conduction couldn't explain them. Now, to understand what was really going on, we need to dip back into the quantum mechanics that was being developed in exactly this period, the 1920s and 30s. And I know quantum mechanics sounds intimidating, but the piece we need here is actually surprisingly intuitive once you see the analogy. So let's build it up. Think about a single atom. Its electrons can only exist at specific energy levels, not any energy they want, but particular, discrete values, like rungs on a ladder. An electron can be on this rung or that rung, but never in between. That's quantum mechanics at its most basic. Now, when you bring two atoms close together, their energy levels interact and split. Where you had one rung, now you have two, very close together. Bring three atoms together, you get three levels. Bring a trillion atoms together, which is roughly what you have in a small crystal, and those individual levels smear out into continuous bands. Broad swaths of energy where electrons are allowed to exist, separated by gaps where they're not. Those gaps are called band gaps, and they turn out to be the single most important concept in understanding why materials behave so differently from each other electrically. Here's the picture. In any solid, you've got a valence band. That's the band of energies where the outermost electrons normally sit, the ones involved in bonding. And above it, separated by the band gap, you've got the conduction band, the range of energies where electrons are free to move through the material and carry current. In a metal, these bands overlap. There's no gap at all. Electrons can freely move into conducting states, which is why metals are such good conductors. In an insulator like diamond, the band gap is enormous, around 5.5 electron volts. That's a huge energy barrier. At room temperature, virtually no electrons have enough thermal energy to jump across that gap, so diamond doesn't conduct electricity. It just sits there, stubbornly insulating. But semiconductors, and this is what makes them special, have a band gap that's small. Silicon's band gap is about 1.1 electron volts. Germanium's is around 0.7, small enough that at room temperature, a few electrons do have enough thermal energy to jump across. Not many, but some. So you get a trickle of conductivity. Not a metal, not an insulator, something in between. And here's what's really clever, that conductivity increases as you heat the material up because more electrons get enough energy to make the jump. That's the opposite of metals, where conductivity decreases with temperature. This was one of the early clues that something fundamentally different was going on. The theoretical framework for all of this came together through the work of several physicists in the late 20s and early 30s. Felix Bloch, working with Werner Heisenberg in Leipzig, developed the theory of electrons in periodic crystal lattices in 1928, his doctoral thesis, remarkably. Alan Wilson at Cambridge refined this into a clear band theory of solids in 1931, explicitly explaining the difference between metals, insulators, and semiconductors in terms of band structure. Rudolf Peierls contributed important work on how electrons behave near band edges. These were young men, mostly in their 20s, building on the brand-new quantum mechanics of Schrödinger and Heisenberg, and within just a few years they had a theoretical framework that explained something people had been confused about for decades. But theory is one thing. Making semiconductors actually do something useful. That required understanding impurities, and this is where the story gets really interesting. Because it turns out that the magic of semiconductors isn't in the pure material. It's in what happens when you deliberately contaminate it. Think about a silicon crystal. Each silicon atom has 4 valence electrons, and in the crystal, each atom shares those 4 electrons with its 4 neighbors in covalent bonds. Everything is tidy, paired up, accounted for. Now imagine you replace one silicon atom with a phosphorus atom. Phosphorus has 5 valence electrons. 4 of them participate in bonding with the neighboring silicon atoms just fine. But that 5th electron has nothing to bond with. It's loosely attached to the phosphorus atom, and it doesn't take much energy at all to set it free, far less than the full band gap energy. So at room temperature, that extra electron easily pops into the conduction band and can carry current. You've just created what's called an N-type semiconductor, N for negative, because you've added extra negative charge carriers. The phosphorus atom is called a donor because it donates an electron. Now, do the opposite. Replace a silicon atom with a boron atom. Boron has only 3 valence electrons. It can bond with 3 of its 4 silicon neighbors, but the 4th bond has a missing electron, a hole. And here's the beautiful part. A neighboring electron can jump over to fill that hole, but in doing so, it leaves a new hole behind. That hole effectively moves through the crystal, and it behaves exactly like a positive charge carrier. This is a p-type semiconductor, P for positive. The boron is an acceptor because it accepts an electron and creates a mobile hole. This idea that you could have 2 types of charge carriers, electrons and holes, and that you could control their concentrations by adding tiny amounts of specific impurities, was the key insight that made everything else possible. And the concentrations really are tiny. We're talking about parts per million or even parts per billion. A few atoms of phosphorus scattered among billions of silicon atoms, and the electrical properties change dramatically. It's like adding a pinch of salt to a swimming pool and completely changing how the water behaves. Except in this case, it actually works. Now, when you put a region of N-type semiconductor right next to a region of P-type semiconductor, something remarkable happens at the junction. The extra electrons from the N side and the holes from the P side diffuse toward each other and recombine near the boundary, creating a thin region that's been swept clean of mobile charge carriers. This is called the depletion zone, and it acts like a tiny barrier. It's why a p-n junction rectifies. Current flows easily in one direction, pushing carriers across the junction, but the depletion zone blocks current in the other direction. And just like that, you've explained the cat's whisker detector. That finicky contact between the metal wire and the crystal surface was creating a crude, accidental p-n junction. The physics was there all along. People just didn't have the framework to see it. The person who probably did more than anyone to bridge the gap between semiconductor theory and practical devices was William Shockley, and his story is one of those complicated ones where brilliance and ambition and deeply problematic personal qualities all get tangled together. Shockley was born in London in 1910 to American parents, grew up in Palo Alto, yes, that Palo Alto, and earned his PhD from MIT in 1936. He joined Bell Telephone Laboratories, which was at that time arguably the greatest industrial research lab in the world, and he became obsessed with the idea of building a solid-state amplifier to replace vacuum tubes. Vacuum tubes worked, but they were fragile. They ran hot. They burned out. They consumed enormous power. The telephone network ran on them, and Bell Labs was spending a fortune on maintenance and replacement. If you could build an amplifier out of a small, cold, durable piece of semiconductor material, it would change everything. The war interrupted things as it did for everyone. Shockley worked on radar and anti-submarine warfare operations research, but after the war, in 1945, Bell Labs assembled a semiconductor research group under Shockley's direction, and the team included 2 people whose names would become inseparable from what happened next: John Bardeen and Walter Brattain. Bardeen was the theorist. Quiet, unassuming, so soft-spoken that people sometimes had to lean in to hear him, but possessed of one of the most powerful analytical minds in 20th century physics. He's the only person ever to win 2 Nobel Prizes in physics, which gives you some sense of the caliber of mind we're talking about. Brattain was the experimentalist, hands-on, practical, the kind of person who could coax a piece of equipment into doing things it wasn't designed to do. Together, they made an extraordinary team. Shockley's initial idea for a solid-state amplifier was something called a field effect device. The concept was straightforward. Put a semiconductor slab between 2 electrodes, apply a voltage to a third electrode sitting above the surface, and use that voltage to control the flow of current through the slab. It should have worked based on the theory. But it didn't. They tried it, and the effect was far smaller than predicted. Something was happening at the surface of the semiconductor that was trapping charge carriers and screening out the applied electric field. Bardeen figured out what it was: surface states, energy levels that existed at the crystal surface and captured electrons before they could respond to the external field. It was a brilliant piece of theoretical detective work, and it redirected the entire research effort. Because once they understood the surface problem, Bardeen and Brattain started experimenting with ways to work around it. They tried different surface treatments, different configurations, and on December 16, 1947, in a laboratory at Bell Labs in Murray Hill, New Jersey, Brattain pressed 2 closely spaced gold contacts into the surface of a small slab of germanium, and Bardeen's circuit design allowed them to demonstrate power amplification. A small signal applied to one contact controlled a much larger current flowing through the other. It worked. It actually worked. They had built the first transistor, the point contact transistor, they called it, and it was ugly, honestly, a crude little thing. 2 strips of gold foil pressed into a germanium crystal, held in place by a plastic wedge glued to a spring. It looked like something you'd build in a garage, not something that would reshape civilization. But it amplified a signal. A small electrical whisper going in, a louder version coming out. And that was everything. Now, here's where the human drama gets really interesting, because what happened next at Bell Labs wasn't just a story about physics. It was a story about ego, credit, and ambition, and it's one of the most painful episodes in the history of modern technology. When Bardeen and Brattain demonstrated their transistor, Shockley wasn't in the room. He was their boss, the leader of the semiconductor group, and the whole project had started from his ideas. But the breakthrough, the actual device that worked, came from Bardeen's theoretical insight about surface states and Brattain's experimental skill. And Shockley knew it. He knew that when the patents were filed, his name wouldn't be on the point contact transistor. It ate at him. By all accounts, Shockley was brilliant, but also fiercely competitive, the kind of person who needed to be the smartest one in the room. So he did something remarkable. Over the next few weeks, working largely alone, often in hotel rooms while traveling, Shockley conceived of an entirely different and fundamentally better transistor design, the junction transistor. Instead of relying on those finicky point contacts pressed into a surface, Shockley's design used 3 layers of semiconductor material sandwiched together. Picture it like a sandwich. A thin layer of one type of doped semiconductor, say P-type, between 2 layers of the other type, N-type, or the reverse, NPN. The current flowing between the 2 outer layers, through the thin middle layer, could be controlled by a small voltage applied to that middle layer. It was elegant, it was robust, and it worked on principles that were much easier to manufacture reliably than those delicate gold point contacts. Shockley wrote up his junction transistor theory in January 1948, barely a month after Bardeen and Bratton's demonstration. But Bell Labs actually kept the whole thing secret for months. They didn't announce the transistor publicly until June 30th, 1948, and when they did, the press release was carefully managed. Shockley made sure he was prominently featured, even though the point contact transistor was Bardeen and Bratton's work. There's a famous photograph from that announcement. Shockley seated at the bench, looking through a microscope, with Bardeen and Bratton standing behind him. It looks like Shockley is the lead inventor, and the other two are his assistants. The reality was almost the opposite. And that photograph, that deliberate staging, tells you a lot about the dynamics in that group. The relationship deteriorated. Shockley began cutting Bardeen and Bratton out of semiconductor research, reassigning them to other projects. Bardeen, who was quiet and dignified, but nobody's fool, eventually left Bell Labs in 1951 to join the University of Illinois, where he went on to develop the theory of superconductivity, BCS theory, which won him his second Nobel Prize. Think about that. He left because the working environment had become intolerable, and then he went and won another Nobel. Bratton stayed at Bell Labs but was moved away from transistor work. The three of them shared the 1956 Nobel Prize in Physics for the transistor, and by all accounts, the ceremony was civil but cool. They were bound together by history, but divided by how that history had played out. But let's come back to the materials science, because the junction transistor, Shockley's design, is where the real materials challenges emerged, and those challenges drove the next several decades of innovation. The junction transistor required something the point contact transistor didn't. Very precise control over the doping profile inside the semiconductor. You needed to create distinct regions of N-type and P-type material within a single crystal, with sharp boundaries between them. And you needed that thin middle layer, the base, to be really thin. Because the thinner it was, the faster the transistor could switch, and the better it performed. In the early 1950s, making junction transistors was painstaking. One method, called grown junction, involved pulling a crystal from a melt and changing the dopant concentration during growth. You'd start with, say, N-type material, then add a P-type dopant to the melt so the crystal transitioned to P-type, then switch back. It worked, but the control was crude. The boundaries between regions were gradual rather than sharp, and the base layer was hard to make thin enough. Another method, alloy junction, involved placing small pellets of a dopant material on either side of a thin semiconductor wafer and heating the whole thing until the pellets melted into the surface, creating doped regions, better, but still limited. The real breakthrough in manufacturing came from a process called diffusion. If you expose the surface of a silicon crystal to a gas containing a dopant, say phosphorus or boron, at high temperature, those dopant atoms will gradually diffuse into the crystal, migrating from the surface inward. The depth of penetration depends on temperature and time, and you can control it precisely. This was the key. By masking certain areas of the surface, protecting them from the dopant gas, and exposing others, you could selectively dope specific regions of the crystal. And by doing multiple diffusion steps with different dopants, you could build up the layered NPN or PNP structure of a junction transistor with much better control than any previous method. Now, here's where an unsung hero enters the story. Jean Herney, a Swiss-born physicist working at Fairchild Semiconductor in the late 1950s, came up with something called the planar process. And this is one of those ideas that sounds simple in retrospect, but changed absolutely everything. Herney realized that if you grew a thin layer of silicon dioxide, basically glass, on the surface of a silicon wafer, that oxide layer could serve as both a protective coating and a mask for diffusion. Silicon dioxide is remarkably good at blocking dopant atoms. So you grow your oxide, etch windows in it where you want to dope, diffuse your dopant through those windows, then grow another oxide layer, etch new windows, and diffuse again. Each step builds up the transistor structure, and the oxide protects everything you've already done. The beauty of this is that the entire transistor ends up buried under a protective glass layer, with only the electrical contacts exposed. That made the devices far more reliable. No more exposed junctions that could be contaminated by dust or moisture. Herney filed his patent for the planar process in 1959, and it's no exaggeration to say that this single idea made the modern electronics industry possible. Because here's the thing, the planar process wasn't just a better way to make one transistor. It was a way to make many transistors on the same piece of silicon, all at once, using the same sequence of steps. You could pattern hundreds, then thousands, then millions of transistors side by side on a single wafer, and they'd all be formed simultaneously. Which brings us to the integrated circuit, and now we've got two people to talk about. Because this is another one of those cases where the same idea occurred to two brilliant minds, almost simultaneously. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor both independently conceived of putting multiple electronic components, transistors, resistors, capacitors, on a single piece of semiconductor material, connected together to form a complete circuit. Kilby got there first, demonstrating a working integrated circuit in September 1958. His version was made of germanium, and the components were connected by tiny gold wires, hand-bonded, delicate, not really suitable for mass production. But it proved the concept. Noyce, building on Herney's planar process, figured out how to do the same thing in silicon with all the connections made by depositing thin metal lines on the oxide surface. No hand wiring. Everything photolithographically patterned. Noyce's approach was the one that scaled, the one that became the foundation of the entire semiconductor industry. And this is really where materials science and manufacturing process become completely inseparable. Because the integrated circuit isn't just a clever design idea, it's a materials achievement. Every step in making a chip is a materials science problem. Growing a perfect single crystal of silicon, that's crystal growth, thermodynamics, defect control. The oxide layer, that's understanding the chemistry of silicon oxidation, the kinetics of how it grows, the electrical properties of the resulting film. Photolithography, that's polymer chemistry, because the photoresist you use to pattern the oxide is a carefully engineered polymer that changes its solubility when exposed to light. Etching, that's chemistry and plasma physics. Metal deposition, that's thin film science. Understanding how atoms land on a surface and form a conducting layer. Ion implantation, which eventually replaced diffusion for doping. That's accelerator physics applied to materials modification. Every one of these steps involves materials behaving in ways that had to be understood, controlled, and optimized. And the tolerances are extraordinary. By the 1970s, the features on a chip were a few micrometers wide, a few millionths of a meter. By the 1990s, they were down to fractions of a micrometer. Today, the most advanced chips have features measured in nanometers, billionths of a meter. We're talking about structures where a line of atoms, literally a few dozen atoms wide, has to be placed exactly where it's supposed to be, billions of times over, on a chip the size of your fingernail. And this relentless shrinking, this is Moore's law in action. Gordon Moore, another Fairchild alumnus who co-founded Intel with Noyce, observed in 1965 that the number of transistors on a chip seemed to double roughly every year or two. It wasn't a law of physics. It was an observation about the pace of engineering progress driven by continuous improvements in materials processing. And for over 50 years, the industry managed to keep up that pace, which is just staggering when you think about it. Every generation of chips required new materials, new processes, new solutions to problems that didn't even exist a few years earlier. Take the gate oxide, for instance, the thin insulating layer in a transistor that separates the gate electrode from the channel where current flows. For decades, this was silicon dioxide, and it worked beautifully. But as transistors shrank, the oxide had to get thinner and thinner to maintain the electrical coupling between the gate and the channel. By the early 2000s, the oxide was down to about 5 atomic layers thick, 5 layers of atoms. At that thickness, quantum mechanical tunneling becomes a serious problem. Electrons just tunnel right through the barrier, creating leakage current that wastes power and generates heat. The solution was to replace silicon dioxide with a different material, a so-called high-K dielectric, hafnium dioxide, introduced by Intel in 2007. Hafnium dioxide has a higher dielectric constant than silicon dioxide, which means you can use a physically thicker layer while getting the same electrical effect. Thicker layer, less tunneling, problem solved. But integrating a new material into a manufacturing process that had been optimized for silicon dioxide over 40 years, that was an enormous materials science challenge. The interface between hafnium dioxide and silicon had to be controlled at the atomic level. New defects, new failure modes, new chemistry to understand. And that's just one example. The story of semiconductor scaling is really a story of materials scientists solving one impossible problem after another, each solution creating the next problem, in this incredible chain of innovation that gave us the computing power we carry around in our pockets today. Your phone has more transistors in it than there are stars in the Milky Way. Something like 15 billion transistors in a modern processor, each one a tiny structure of precisely doped silicon, insulating oxides and metal interconnects, all built up layer by layer through processes that would have seemed like pure science fiction to Bardeen and Bratton back in that lab in 1947. But semiconductors, as extraordinary as they are, represent just one thread in the larger materials science story. And there's another class of materials that emerged in the 20th century that took a completely different approach to achieving extraordinary properties, not by perfecting a single substance, but by combining 2 or more materials together in ways that exploit the best qualities of each. These are composites, and the idea behind them is actually older than you might think. Nature figured it out long before we did. Wood is a composite. Cellulose fibers embedded in a matrix of lignin. Bone is a composite. Collagen fibers reinforced with hydroxyapatite crystals. Even mud brick, one of humanity's oldest building materials, is a composite. Clay reinforced with straw. The idea is beautifully simple. You take one material that's good at one thing, and you embed it in another material that's good at something else. And if you do it right, the combination has properties that neither material could achieve on its own. Think about fiberglass, which is probably the composite most people have encountered in everyday life. Glass, as we know, is strong, but brittle. It'll hold a lot of force, but when it breaks, it shatters. Polyester resin, on the other hand, is flexible but not particularly strong on its own. But if you take thin fibers of glass and embed them in that resin, something remarkable happens. The glass fibers carry the load. They're the structural backbone. The resin holds the fibers in place, distributes stress between them, and protects them from damage. And here's the clever part. If a crack starts in one fiber, it can't easily jump to the next fiber because the resin between them absorbs the energy and stops the crack from propagating. Remember how we talked about Griffith's flaw theory, the idea that cracks concentrate stress at their tips? In a composite, the matrix material blunts those crack tips. It interrupts the catastrophic chain reaction that makes brittle materials fail so suddenly. So you end up with something that has the strength of glass but the toughness of plastic, best of both worlds. The modern era of high-performance composites really begins with carbon fiber, and the story of how carbon fiber came to be is one of those wonderful tales of parallel invention and stubborn persistence. In the late 1950s and early 1960s, researchers in several countries were independently trying to figure out how to make strong fibers from carbon. The appeal was obvious. Carbon can form incredibly strong bonds, and if you could get carbon atoms lined up just right, in long chains or sheets, you'd have a fiber that was both incredibly strong and incredibly light, much lighter than steel, much lighter even than aluminum. One of the key figures was a British engineer named William Watt, working at the Royal Aircraft Establishment in Farnborough, England. In the mid-1960s, Watt and his colleagues Leslie Phillips and William Johnson developed a process for making high-strength carbon fibers from a precursor material called polyacrylonitrile, PAN for short. PAN is basically a type of acrylic polymer, the same family of materials used in some synthetic fabrics. The process involves heating the PAN fibers in a carefully controlled sequence, first in air at around 200 to 300 degrees Celsius, which stabilizes the molecular structure, and then in an inert atmosphere at much higher temperatures, over 1,000 degrees, sometimes up to 3,000 degrees Celsius. During this high-temperature treatment, the non-carbon atoms are driven off, and the remaining carbon atoms rearrange themselves into graphite-like sheets, aligned along the fiber axis. The result is a fiber that's about 5 to 10 micrometers in diameter, thinner than a human hair, but with a tensile strength that can exceed that of steel while weighing a fraction as much. Now, here's what's really interesting about this from a materials science perspective. The properties of the carbon fiber depend enormously on exactly how you process it. The temperatures, the heating rates, the tension applied during carbonization. Higher temperatures tend to increase the stiffness of the fiber by improving the alignment of those graphite sheets, but they can actually reduce the ultimate strength. So there's a trade-off, and you can tune the process to get different grades of carbon fiber for different applications. This is that central dogma we keep coming back to. Processing determines structure. Structure determines properties. Same starting material, different processing, dramatically different results. But carbon fiber by itself is just a fiber. To make it useful, you need to embed it in a matrix, just like fiberglass. The most common matrix materials for carbon fiber composites are epoxy resins, thermosets, like the bakelite we talked about earlier, that cure into a rigid, cross-linked network. The carbon fibers provide strength and stiffness. The epoxy holds everything together, transfers loads between fibers, and gives the part its shape. And because you can control the orientation of the fibers, laying them in specific directions, at specific angles, You can engineer the material to be strong exactly where you need it to be strong. This is something metals simply can't do. A sheet of aluminum is more or less equally strong in every direction. But a carbon fiber composite can be designed to be incredibly strong along one axis and more flexible along another. Engineers call this anisotropy, and it's both the great advantage and the great challenge of working with composites. The aerospace industry was the first to really embrace carbon fiber composites in a serious way, and for obvious reasons. In aviation, every kilogram you save translates directly into fuel efficiency, range, and payload capacity. Military aircraft led the way. The F-18 Hornet, which first flew in 1978, used carbon fiber composites in its wing skins and tail surfaces. But the real watershed moment for commercial aviation came decades later, with the Boeing 787 Dreamliner, which entered service in 2011. The 787 is roughly 50% composite by weight. The entire fuselage is made from carbon fiber reinforced polymer, laid up in huge sections using automated tape-laying machines that place strips of pre-impregnated carbon fiber, called pre-preg, onto molds with extraordinary precision. This was a massive gamble by Boeing. No one had ever built a commercial airliner fuselage from composite materials at that scale. The engineering challenges were immense. One of the trickiest problems was understanding how composites fail. With metals, we have decades of fatigue data. We know how cracks initiate, how they grow, when they'll become critical. Remember Wöhler and his railroad axles? All those careful experiments mapping out how metals behave under repeated loading? With composites, the failure modes are completely different and much more complex. Instead of a single crack growing through the material, composites can fail through fiber breakage, matrix cracking, delamination, where layers separate from each other, or fiber pullout, where fibers slide out of the matrix. Often, multiple failure modes interact simultaneously. A small impact, say a tool dropped on a composite panel during maintenance, might cause internal delamination that's invisible on the surface but significantly reduces the part's strength. This is sometimes called barely visible impact damage, and it's one of the reasons composite structures require different inspection techniques than metal ones. You can't just look at a composite panel and see if it's damaged the way you sometimes can with metal. You need ultrasonic inspection, thermography, or other non-destructive testing methods to find hidden damage. And then there's the question of how composites behave over the long term. Metal fatigue is well understood because we've been studying it for over 150 years. Composite fatigue is still an active area of research. The good news is that carbon fiber composites generally have excellent fatigue resistance, in many cases better than the aluminum alloys they replace. But the failure mechanisms are different enough that the aerospace industry had to develop entirely new certification frameworks, new testing protocols, new design philosophies. The damage tolerance approach that George Irwin's work made possible for metals had to be reimagined for composites. So, why go through all that trouble? Because the weight savings are transformative. Boeing claims the 787 uses about 20% less fuel than comparable conventional aircraft. Over the lifetime of an airplane, and commercial aircraft can fly for 30 years or more, that's an enormous amount of fuel, an enormous amount of money, and an enormous reduction in carbon emissions. The material made the design possible. But here's the thing about composites that doesn't get talked about as much. They've also quietly revolutionized much more mundane parts of everyday life. Wind turbine blades are made from fiberglass, and increasingly carbon fiber composites. because they need to be both strong and light enough to catch the wind efficiently. Modern wind turbine blades can be over 100 meters long, longer than a football field, and they're essentially giant composite structures, carefully engineered to flex without breaking, to resist fatigue from millions of load cycles as they spin year after year. Without composite materials, renewable wind energy at the scale we see today simply wouldn't be practical. Sports equipment is another area where composites transformed what's possible. Tennis rackets, golf club shafts, bicycle frames, fishing rods, hockey sticks, all increasingly made from carbon fiber composites. And it's not just about making things lighter, though that matters. It's about being able to tune the stiffness and vibration characteristics of the equipment in ways that weren't possible with wood or metal. A carbon fiber bicycle frame can be engineered to be stiff in the bottom bracket area, where you want efficient power transfer from your pedals, but more compliant in the seat stays, where you want some give to absorb road vibrations. That kind of selective engineering of mechanical properties is uniquely enabled by composites, and composites keep evolving. One of the most exciting frontiers is in self-healing materials, composites that contain microcapsules filled with a healing agent, a liquid resin, distributed throughout the matrix. When a crack forms and ruptures one of these capsules, the healing agent flows into the crack and polymerizes, essentially gluing the crack shut. The concept was demonstrated by Scott White and his team at the University of Illinois in 2001, and while it's still mostly in the research phase for structural applications, the underlying idea is extraordinary. A material that can repair itself, the way your skin heals a cut. It sounds like science fiction, but it's really just materials science, understanding chemistry and microstructure well enough to design a response into the material itself. There's also growing interest in bio-inspired composites, materials that mimic the hierarchical structures found in nature. Nacre, the iridescent material on the inside of abalone shells, is a natural composite of aragonite platelets, a form of calcium carbonate, layered with thin sheets of organic polymer. It's about 3,000 times tougher than aragonite alone, because those organic layers deflect and absorb cracks, forcing them to follow tortuous paths that dissipate energy. Researchers are now trying to replicate this kind of architecture synthetically, using techniques like freeze casting and additive manufacturing to build up materials with controlled microstructures at multiple length scales. The idea is that by mimicking the way nature organizes relatively weak building blocks into remarkably tough structures, we can create new materials that are both strong and damage-resistant without relying on expensive fibers or energy-intensive processing. And this brings us to something that's been quietly reshaping the entire field of materials science over the last couple of decades. The idea that we don't have to just discover materials by trial and error anymore. For most of human history, finding new materials was a slow, painstaking process. You'd mix things together, heat them up, test them, and see what happened. Sometimes you'd get lucky. Sometimes you'd spend years on a dead end. But what if you could predict the properties of a material before you ever made it? What if you could simulate the behavior of atoms and molecules on a computer, screen thousands or even millions of possible compositions, and identify the most promising candidates before anyone steps into a lab? This is the promise of computational materials science, and it's already changing everything. The basic idea is actually pretty intuitive once you think about it. You know how we talked about the way atoms arrange themselves in crystal lattices, the way iron switches from body-centered cubic to face-centered cubic when you heat it, and how that rearrangement changes everything about the material's properties. Well, the forces that govern those arrangements, the quantum mechanical interactions between electrons, the electrostatic pushes and pulls between charged particles, those forces are described by equations. Incredibly complicated equations, sure, but equations nonetheless. And if you can solve those equations accurately enough, you can predict how a given collection of atoms will arrange itself, how stable that arrangement will be, and what properties the resulting material will have. You don't need to melt anything. You don't need a furnace or a rolling mill or a tensile testing machine. You just need math and a fast enough computer. The roots of this go back further than you might expect. In the 1920s and 1930s, right around the time Taylor, Orowin, and Polanyi were figuring out dislocations, physicists like Erwin Schrödinger and Paul Dirac were laying down the quantum mechanical framework that describes how electrons behave in atoms and solids. Dirac famously said in 1929 that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry were completely known, and that the difficulty was only that the exact application of these laws led to equations much too complicated to be soluble. He was right on both counts. The physics was understood, but the math was, for practical purposes, impossible to solve exactly for anything more complex than a hydrogen atom. A single hydrogen atom, one proton, one electron. That's it. Anything bigger than that, and you're dealing with what physicists call the many-body problem, where every electron interacts with every other electron and every nucleus simultaneously, and the computational complexity explodes. So for decades, computational approaches to materials science were limited to simplified models and approximations. People could do useful things, calculate the elastic properties of simple crystals, estimate the energies of different crystal structures. But the dream of designing new materials from first principles, starting from nothing but the periodic table and the laws of physics, remained out of reach. The breakthrough that changed this, more than any other single development, was density functional theory, or DFT. It was developed in the 1960s by Walter Kohn and Pierre Hohenberg, and then made practically useful by Kohn and Liu Zhu Sham. What they showed was that instead of trying to track the behavior of every single electron individually, which is what makes the many-body problem so intractable, you could reformulate the whole problem in terms of the electron density, which is just a measure of how many electrons are in each region of space. This sounds like a subtle mathematical trick, and in some ways it is, but the consequences are enormous. Instead of solving equations for, say, 100 electrons all interacting with each other, which involves a function in 300 dimensions, you solve equations for the electron density, which is a function in just 3 dimensions. 3. The same 3 spatial dimensions you and I live in. That's a staggering simplification. Kohn won the Nobel Prize in Chemistry for this in 1998, and by then DFT had already become the workhorse of computational materials science. By the early 2000s, researchers could routinely calculate the properties of crystals with a few dozen atoms in the unit cell. Things like band gaps, elastic constants, magnetic properties, phase stability, with remarkable accuracy. Not perfect accuracy, mind you. DFT involves approximations of its own, and there are certain properties it struggles with. But for a huge range of materials questions, it gives you answers that are good enough to be genuinely useful. Here's where it gets really exciting, though. Calculating the properties of one material is interesting. Calculating the properties of 10,000 materials is transformative. And that's exactly what started happening in the late 2000s and 2010s, driven by a combination of faster computers, better algorithms, and, this is the key part, a philosophical shift in how people thought about materials discovery. The person most associated with this shift is Gerbrand Cedar at MIT, later at Berkeley, who in the mid-2000s started building what he called the Materials Project, a massive open-access database of computed material properties. The idea was simple but ambitious: systematically calculate the properties of every known inorganic compound, and then make all that data freely available to anyone in the world. By the time the Materials Project launched publicly in 2011, it contained computed data on tens of thousands of materials. Today, it covers well over 100,000 compounds, and it's been used by researchers all over the world to identify new battery materials, new catalysts, new thermoelectrics, new alloys. Think about what that means for the central dogma we talked about early on. Composition plus processing gives you structure. Structure gives you properties. What computational materials science does is let you explore that relationship at a speed and scale that would be physically impossible in a lab. You want to know what happens if you take a known crystal structure and substitute one element for another? You can compute that in hours, instead of spending months synthesizing and testing. You want to screen every possible combination of three elements that might form a stable compound with a band gap in a certain range? You can set up that calculation and let it run. It's not replacing experimental work. You still need to actually make the material and verify that it behaves the way the computation predicts. But it's radically narrowing the search space. Instead of looking for a needle in a haystack, you're looking for a needle in a small box that a computer has already told you probably contains needles. And this connects beautifully to machine learning, which has come roaring into material science over the last decade. The idea here is that once you have large databases of material properties, whether computed or measured experimentally, you can train machine learning models to recognize patterns in that data, patterns that might be invisible to a human researcher. You feed the model thousands of examples of materials with known properties, and it learns to predict the properties of materials it's never seen before, based on their composition and structure. Some of the early successes have been remarkable. In 2016, a team at Stanford used machine learning to predict the stability of new perovskite compounds. Perovskites being a family of crystal structures that are incredibly important for solar cells and other energy applications. They screened over 100,000 hypothetical compositions and identified several hundred promising candidates, many of which were subsequently confirmed experimentally. Now, you might be thinking, this all sounds very abstract. What does it actually mean for the real world? And that's a fair question. So let me give you a concrete example that ties together a lot of what we've talked about tonight. Batteries. Specifically, lithium-ion batteries. The kind in your phone, your laptop, probably an electric car in your neighborhood. The performance of a lithium-ion battery depends critically on the materials used in its cathode, the positive electrode. For years, the dominant cathode material was lithium cobalt oxide, which Sony commercialized in 1991. It works well, but cobalt is expensive, it's toxic, and most of the world's supply comes from the Democratic Republic of Congo, where mining conditions are often horrific. So there's been enormous motivation to find cathode materials that use less cobalt or no cobalt at all while maintaining or improving performance. This is exactly the kind of problem where computational materials science shines. Researchers have used DFT calculations and machine learning to screen thousands of potential cathode compositions, looking for materials that can store a lot of lithium ions, that are stable over many charge-discharge cycles, that conduct ions quickly, and that don't rely on cobalt. One of the most promising results has been the development of high-nickel cathodes and lithium iron phosphate cathodes, both of which were identified and optimized with significant help from computational screening. The lithium iron phosphate story is particularly nice because it was originally considered a poor cathode material. It didn't conduct electrons or ions well enough. But computational work helped researchers understand exactly why, and that understanding led to processing innovations, nanostructuring the particles, coating them with carbon, that overcame the limitations. Today, lithium iron phosphate batteries are in millions of electric vehicles worldwide. They're cheaper, safer, and more durable than cobalt-based alternatives, and they exist in their current form partly because computational tools helped scientists understand and engineer around their weaknesses. There's something deeply satisfying about that arc, if you think about it. We started tonight talking about the most basic question in materials science. Why do materials have the properties they have? And the answer, every single time, comes back to structure. The arrangement of atoms, the nature of the bonds between them, the defects, the grain boundaries, the phases, the microstructure at every length scale from the atomic to the macroscopic. And for thousands of years, humans figured this out by smelting, hammering, quenching, mixing, breaking, and trying again. The blacksmith who discovered that quenching hot steel in water made it hard didn't know about martensite or body-centered tetragonal crystal structures. The ancient Mesopotamians who reinforced mud bricks with straw didn't know about composite mechanics or crack bridging. But they were doing materials science. They were manipulating structure to control properties, even if the language to describe what they were doing wouldn't exist for millennia. And then, piece by piece, the understanding caught up with the practice. Sorby looked through his microscope and saw the microstructure of steel for the first time. Gibbs wrote down the thermodynamic framework that explained phase diagrams. Griffith figured out why materials fail at stresses far below their theoretical strength. Staudinger proved that polymers were real molecules, not mysterious colloids. Bardeen and Bratton touched a gold contact to a germanium surface and invented the transistor. Each of these moments was a step toward the same destination, a deep enough understanding of how matter organizes itself that we could begin to design materials intentionally, rationally, with specific properties in mind. And now we're entering an era where that design process is accelerating in ways that would have seemed unimaginable even 20 years ago. Materials informatics platforms are combining experimental data, computational predictions, and machine learning to suggest entirely new materials for specific applications. Additive manufacturing, 3D printing, essentially, is making it possible to build objects with spatially varying compositions and microstructures, so a single part can be hard on the outside and tough on the inside, or stiff in one direction and flexible in another. Remember how we talked about the anisotropy of carbon fiber composites, how the properties depend on the direction of the fibers. Additive manufacturing takes that idea and generalizes it. You can design the internal architecture of a material the way an engineer designs a bridge, putting strength where you need it and saving weight where you don't. And those bio-inspired materials we were just talking about, the ones that mimic nacre or bone. Additive manufacturing is one of the key technologies making them possible. You can print layers of ceramic and polymer in controlled patterns, building up the kind of hierarchical structures that nature uses, but with synthetic materials and engineered precision. It's the convergence of computational design, advanced manufacturing, and a century of accumulated understanding about structure-property relationships. It's all coming together. But here's the thing I want to leave you with, and it's something that I think is genuinely beautiful about materials science as a field. For all the computational power, for all the machine learning and simulation and high-throughput screening, the fundamental questions haven't changed. They're the same questions that a curious person asked the first time they noticed that a copper blade held an edge differently than a stone one. Why is this material different from that one? What's happening inside it that makes it behave this way? And can I change it? Those questions led us from the Bronze Age to the Steel Age to the Silicon Age, and wherever we're headed next. Some people call it the Materials Age, which feels right. Those same questions will be at the center of it. The tools are incomparably more powerful now. The understanding is deeper. But the curiosity is the same. It's the same impulse that made someone, thousands of years ago, pick up a piece of iron meteorite and wonder what it was, why it was so different from the rocks around it, and what they could make from it. So, as you drift off tonight, maybe carry that thought with you. Every material you touch today, the glass of your phone screen, the steel in your car, the polymer in your toothbrush, the silicon in every chip in every device around you. Every one of those materials has a story. A story of atoms arranging themselves, of humans figuring out how to coax those arrangements into something useful, of failures that taught us more than successes ever could, and of a slow, patient accumulation of understanding that connects a Roman blacksmith to a modern computational scientist in an unbroken chain of curiosity. That's materials science. And it's been quietly shaping every part of your world all along, whether you noticed it or not. Rest well. The atoms will still be there in the morning, doing exactly what they've always done, arranging themselves, bonding, breaking, rearranging, building the world one structure at a time,